Hello, I'm Dr. DeBellis. Now that we've talked about neuroanatomy and the basics of biological psychology, I'd like to talk to you about neurophysiology. Neurophysiology is the study of the life processes within neurons. Neurons use electrical and chemical signals, and we're going to talk about how they do that to convey messages to other neurons. In order to understand the steps in neurophysiology, it's going to be helpful for us to divide it into three stages. First, the graded potential, then the action potential, and finally, synaptic transmission. In order to have a better overview, I recommend the acronym GAS for graded, action, and synaptic. So if you can use that acronym, I think it'll help you to have a better overview of the topic we're talking about. Now, the graded potential occurs primarily in the dendrites and the cell body, which you see down below. The action potential begins in the axon hillock, and it travels, it sort of jumps forward through a phenomenon we're going to call saltatory conduction, along the axon. Here you see the axon extending from the axon hillock. And finally, we're going to talk about synaptic transmission, which occurs primarily in the axon terminals, and here you see the terminal buttons here. It's helpful to think of this sort of like a soccer ball next to some dominoes with a ball at the end. If we can think about the graded potential, which occurs in the cell body as a soccer ball. Instead of air pressure, we're going to talk about electrostatic pressure. And when it builds up high enough, it starts this action potential, which travels like a domino. It travels like dominoes. And finally, it releases a neurotransmitter, which if you saw that yellow ball being bumped off of my table, it's kind of like a neurotransmitter that's being dropped into the synapse where it's going to diffuse to the other side. And then whenever it hits the other side, it's hopefully going to have it's going to help have a graded potential on the next neuron. We're going to talk about this in more detail. The action potential is a rapid electrical signal that travels along the axon of the neuron like dominoes. It jumps down the nodes of Ranvier like dominoes. A neurotransmitter is a chemical messenger which diffuses between neurons in the synaptic cleft. And we're going to talk about many different neurotransmitters. Some hormones are also neurotransmitters. We're going to spend a lot of time talking about the classic biogenic amines, dopamine, which is really important for reward circuits, movements. It's implicated into ADHD and schizophrenia. We're going to talk about acetylcholine, which is really important for the rest and digest response, as well as muscle contractions and cognition. We're also going to talk about serotonin, which has many different roles whenever it comes to neurosis, depression, appetite, sex, pain, and then finally norepinephrine, also called noradrenaline, which plays a very important role in the sympathetic fight or flight response. But these neurotransmitters are produced here in the presynaptic neuron. The presynaptic neuron then releases them into the synapse, and they travel across to the postsynaptic membrane. And when they hit the right receptor, the receptor actually is activated. It's sort of like a key opening a lock, and that lock opens, and it allows an ion to travel in. Now we have two different ions. We have cations, which are positively charged, and anions, which are negatively charged. If just one ion is let in, it's not going to make a world of difference. But when you have symphonies of these, whenever that happens, the combined change in polarity can actually lead to something as significant as an action potential, which we just discussed. Information flows within a neuron via electrical signals that we're going to refer to as action potentials in this class. And while information passes between neurons through chemical signals, we're going to call this neurotransmission. And we're going to investigate the former in more detail in this chapter as we explore the action potential. And we'll also elaborate on the latter in the following chapters. There are two opposing forces we need to discuss before we proceed. These two forces drive ion movement. We have electrostatic pressure and diffusion. You're probably familiar with these two. Electrostatic pressure causes ions to flow towards oppositely charged areas. So everybody's probably taken a pair of magnets and noticed that they are attracted on certain ends, they repel on others. Different charges attract each other. Diffusion, if you've ever made some Kool-Aid, you're aware that whenever you dump a packet of Kool-Aid into a pitcher of water, that the Kool-Aid is going to diffuse across the water. This diffusion in the neuron causes ions to flow from areas of high to low concentration down their concentration gradients. So as Lord Yoda would tell you, important these driving forces are to know. A neuron at rest is a balance of electrochemical forces. So we have ions, which again are electrically charged molecules. Anions are negatively charged and cations are positively charged. Ions are dissolved in intracellular fluid, which is separated from the extracellular fluid by the cell membrane, which is arguably one of the most important structures of the neuron. And if you inserted a microelectrode into a resting neuron, it reveals it's more negative than the extracellular fluid. So for the purpose of this course, the resting membrane potential 60 millivolts, and it shows the negative polarity of the cell's interior. Up above we have this nice neuron. It's a little stuffed animal by Beanie Babies. It was given to me by one of my teaching assistants. But if they had taken my course, perhaps the person who designed this would acknowledge the fact that the neuron is very negative inside. So maybe you could put a frown on it. Okay, Beanie Babies, please get it right. You might be asking, why is it the intracellular space is negative? In order to understand that, I'm going to try to explain it by looking at the little tiny molecules that are actually inside of the neuron and outside of the neuron. So this is the intracellular space at the bottom of your page. I'm going to try to always use the intracellular space at the bottom of the page, and I'm going to try to make the extracellular space at the top of the page. So if we look at the different molecules, I want to first point out the blue molecules are anions. What I mean is the blue molecules have a negative charge. So protein and chloride carry a negative charge. On the other hand, potassium, sodium, and calcium have a positive charge. Now, if we look at this distribution of the different ions, you can see that protein is heavily distributed in the intracellular space. We have only one protein molecule in the extracellular space, but we have 1, 2, 3, 4, 5, 6, 7 in the intracellular space. This is a large reason the intracellular space is negative, and they are not able to typically escape to the extracellular space because they're contained by this powerful membrane that plays a very vital role in restoring the electrical potential of the neuron. We also have chloride. Chloride's more densely distributed in the extracellular space, but there is chloride in the intracellular space. Potassium is not real common in the extracellular space. It is in the extracellular space, but not nearly as much as in the intracellular space. So in the extracellular space, we have 3 potassium molecules. In the intracellular space, I'm counting in this particular situation 11. So there's going to be a much higher density of potassium in the intracellular space. We also have sodium. There's sodium in the intracellular space. I see 4 there. But we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in the extracellular space. So sodium, which like potassium is a positively charged cation, is much more common in the extracellular space than the intracellular space. And finally, we have calcium, which we tend to find more in the extracellular space. It's also positively charged. It's not as abundant in the intracellular space as it is in the extracellular space. Now, if we add to this cell membrane, which is a lipid bilayer, if we add to it these ion channels, so the lipid bilayer is studded with gated and ungated ion channels, and here we see some of these ion channels. They play a really huge role for the membrane. Ion channels are proteins that span the membrane, and they allow ions to pass through like open windows. So an ion can just pass through at any time. The first ion channel we're going to talk about is the potassium channel. But it's just this opening that potassium can go to the intracellular space whenever it wants. It can return to the extracellular space. It's free to do what it would like. Now, gated ion channels are a little more complicated. Gated ion channels have this little receptor here. And this receptor basically is activated by things such as voltage. And it will open and close in response to the voltage changes, as well as chemicals or mechanical action. So here we see it open. And again, once it's open, it will allow a molecule to pass through. So here we are again with the cellular membrane. We have our dense distribution of sodium and calcium on the outside. We have densely populated potassium and protein in the intracellular space. Potassium channels are open all the time, and they allow only potassium ions to cross. So because of this, the neuron shows selective permeability to potassium. We're going to abbreviate potassium as a K. It has a plus sign next to it so that you will be able to remember that it is positively charged. It's a cation. But the neuron shows the selective permeability, so potassium can enter or leave the cell freely. These potassium channels sometimes let sodium in as well. So this is a problem for the neuron because the neuron is trying to remove the sodium from the intracellular space. So here we've added a potassium channel to our cellular membrane. And if the sodium goes in, typically it's not allowed to pass through. It returns. But potassium, on the other hand, it's allowed to travel to the intracellular space. Now, most of the time, sodium's not allowed to enter into the intracellular space, but sometimes it is. The net effect is the extracellular space is going to have lots of sodium, but very little potassium, and the intracellular space is going to have lots of potassium and protein, but very little sodium. At rest, sodium ions move into the negative interior of the cell through ion channels because of the electrostatic pressure. In other words, the negative interior of the neuron attracts the potassium ions. as potassium ions build up inside the cell, they also diffuse out through the membrane down their concentration gradients. So there's such a dense population of potassium in the intracellular space. At some point, the potassium doesn't want to deal with the crowd. It wants to actually go to the more positively charged extracellular space where it has a lower concentration of potassium. Potassium reaches equilibrium when the movement out is balanced by the movement in. This is caused by diffusion pushing the potassium out, while electrostatic pressure, the negative charge in the intracellular space, draws in the positively charged potassium. And at equilibrium, the resting membrane potential is approximately negative 60 millivolts compared to the extracellular space. Now that we've talked about the potassium channel, I would like to talk about the second channel. It's the workhorse of the neuron. It's the sodium-potassium pump, and it will maintain the resting potential. I mentioned earlier that the potassium channels have selective permeability to potassium. However, sometimes sodium does actually sneak in through the potassium channels. This is not good for the neuron, which is trying to maintain its negative resting potential. So whenever the sodium comes in with the potassium leaving, the sodium-potassium pump pumps 3 sodium ions out for every 2 potassium ions pumped in. The mnemonic that I use is, if the cation's okay, let it stay. If it's Na, then send it away. So here we have the cellular membrane again. Over here we have our potassium channel, and here we have our sodium-potassium pump. And they're both working simultaneously. Sodium tries to enter the potassium channel. Oftentimes it's denied. But we see on the right, the sodium-potassium pump is actually taking sodium and it's kicking it out from the intracellular space while it's drawing in potassium. And the potassium channels are allowing the potassium to passively enter. And remember, it's drawn in by the negativity of the intracellular space. However, some of it leaves because of the high concentration of potassium. So potassium channels allow potassium unrestricted travel in and out of the neuron, but sodium-potassium pumps push out 3 sodium ions in exchange for drawing in 2 potassium ions. This is important to know as we proceed, and the potassium channels and the sodium-potassium pumps are the key figures in this graded potential that we're likening to the pumping up of a soccer ball. Now, potassium's initially drawn into the intracellular space by the negative charge, but when too much potassium density builds up, again, it leaves down its concentration gradient, and sodium desperately wants into the neuron because there's a low density of sodium in the intracellular space, as well as sodium's positively charged. It's a cation, so it's drawn to the negative charge of the intracellular space. As cations and anions are transferring from the intracellular space to the extracellular space, we're going to need these 2 terms to make ourselves aware of and to be able to describe the fact that the membrane potential is going to increase and decrease. The charge is constantly going to be fluctuating. Hyperpolarization is an increase in membrane potential, which means the interior of the neuron becomes even more negative. We say it's hyperpolarized because polarized means to become more separate or different. And whenever the intracellular space becomes more negative, it's becoming less positive. And the extracellular space is positive. So hyperpolarization is when the intracellular space becomes even more different in charge than the extracellular space. It becomes more negative on the intracellular space. Depolarization is a decrease in membrane potential. So the interior of the neuron becomes less negative. So the intracellular space becomes less negative. At resting, it's negative 60 millivolts. If it's slightly depolarized, it could be maybe negative 59, negative 58. Eventually, it could become negative 50, negative 45 millivolts. Whenever it reaches negative 40 millivolts, then we're going to talk about the next stage, which is going to be the action potential. A hyperpolarizing stimulus produces a response that passively follows the stimulus. Like a wave, the greater the stimulus, the greater the response. The change in potential is called the graded response. One of the reasons that I use the soccer ball to represent the graded response is because the harder you pump the soccer ball up, the quicker it will actually reach its optimal size. However, whenever we're talking about dominoes, it doesn't matter how hard you push that first domino. The dominoes will still travel at the same rate, and they will still have the same impact on each other. So you can't speed up the way the dominoes will fall, but you can speed up how quickly you pump up the socks. At this time, you might be impressed by the important role of the cellular membrane that it plays in the resting potential. You might even wonder what might happen if a breach in the membrane ever occurred. What if we made a hole in the cellular membrane? What would the consequences be? Well, you probably are wondering whether sodium would be drawn into the intracellular space because of the negative electrostatic pressure. But selective permeability to potassium prevents sodium from entering. So here I have a diagram that I made where I show the charge of the intracellular space during the graded potential. Again, the graded potential is not all or none like the dominoes. The graded potential refers to the constantly fluctuating changes in the intracellular space in the dendrites and the cell body. Here we have depolarization. Then we have hyperpolarization when the charge becomes more negative. And whenever the charge is becoming more positive, again, we have depolarization. Again, here we have the blue. I'm using blue to represent hyperpolarization. But when a lot of cations end up entering the intracellular space, when you've really had a lot of Red Bull, and it causes a really serious depolarization, at some point, and we're going to call that point negative 40 millivolts, that's going to lead to the domino effect that we're going to call the action potential. But what we've described so far is occurring in the cell body as well as in the dendrites. I want you to be cognizant of the fact that the action potential, which we're going to talk about next, that's actually going to be occurring in the axon. And then finally, synaptic transmission is going to occur in the synapses here. So this is a diagram that I've done. We're going to refer to this in the future, but I think you should familiarize yourself with this is the graded potential, everything to the left of this line. I put these A's, B's, and C's here To remind you, this is graded. The more neurotransmitter that hits the dendrites, the larger fluctuation we're going to see in the resting potential, which is usually, again, absolute resting potential is going to be about negative 60 millivolts. Here our y-axis represents the voltage, whereas our x-axis represents the passage of time. Resting potential is about negative 60 millivolts, and threshold is going to be negative 40 millivolts. And when we do hit negative 40 millivolts, that's when we're going to see the action potential, which is pretty exciting. I want you to stay tuned here so we can talk about exactly what happens with the action potential. I also have a version of this chart where I have removed the labels. If you want to print this out or you want to draw a picture of this, I think it's helpful for you to label this yourself. And at this point, you should be able to label the things that are before this vertical line right here. All right, and I've also put a study guide here. Thank you very much, and please view my next PowerPoint presentation, which is actually on the action potential, which is the next stage. Thank you very much.